Yeah.
I'm going to talk to all of you.
You're on, sir.
Okay, well, welcome back, everybody. My name is Dave Richards. I do a lot of the NFPA70E license renewal trainings for the IEC and our company. And anyways, I'm going to give you a drink through a fire hose today. I'm going to give you a lot of information, but we'll try to emphasize the key points that you can use in the field. So, all right. So the whole objective, the reason why we're going over this is to help you have a better understanding of the different types of electrical hazards that we're going to talk about that you can encounter in the workplace, which is arc flash, arc blast, and electrical shock, and to help you get a little bit better understanding of what the NFPA70E is. Okay. So a lot of people, don't know this, but the main hazards with electricity, as you guys, everybody here should know, and by everybody here, I mean you, electrical shock, right? Don't raise your hands, but, think about it. How many of you have had an electrical shock in your career so far? We all have, right? 50% of
they all got a static shock.
Yeah. 50% of electricians have received an electrical shock, and the other 50% are liars. Right. So electrical shock, then there's arc flash. And one of the things that people never think about is the arc blast. We're going to talk about those starting with electrical shock. So does everybody here know what a milliamp is? What year is this? Second year? Third year. So hopefully everybody knows what a milliamp is. What is a milliamp? Any guesses? It's a thousandth of an amp. Thousandths of an amp. That's not much, right? That's not much. Between 2 to 3 thousandths of 1 amp, you'll feel a slight tingling sensation. But once you are exposed to about 9 to 10 thousandths of an amp, that's where you're going to start to feel it. And at 10 to 20 thousandths of an amp, it's going to be very painful. So if you really think about this, like when are your GFCIs designed to trip? If they're working correctly, there's no common neutral problems, things like that. How many milliamps are they supposed to trip at? Any guesses? Yeah, between 4 to 6 milliamps. So if your GFCIs are working correctly and there's no common neutral issues, they should be tripping before you even get to this moderate sensation. But like I said, after that, it becomes very painful. Once you hit about 20 to 30 thousandths of 1 amp, you're going to experience what's called muscular contraction. That's where you're touching an energized circuit part or a live energized conductor, and you can't let go. You're physically locked up. Your brain is saying, we got to let go. We're dying here, but you can't. You just can't. Until your legs give out, maybe gravity pulls you off, something like that. So that's called muscular contraction. And what's going to happen if your coworker grabs you to pull you off? Yeah, he's caught up too, right? After that, you start experiencing some muscular paralysis. Then your respiratory system is affected. Now, this is between 60 to 100 thousandths of 1 amp. We haven't even hit a half an amp yet. That's not much if you think about it. And after that, that's where your heart goes into what's called ventricular fibrillation. Okay, at less than 1 amp. Instead of your heart beating normally like it normally does, pumping vital oxygenated blood to your body and your vital organs, it just sits and quivers in your chest. All the chambers aren't in sync and it's out of order and it just sits and shakes in your chest. And then your vital organs, like your brain, doesn't get the vital oxygenated blood that it needs to survive. And that's where people tend to die. So a fully grown man can die less than 1 amp. Less than 1 amp. That's why your GFCIs are supposed to trip so early, you're not even supposed to feel it. Does that make sense? So it's magic. So what the NFPA70 defines as shock as a source of possible injury or damage to health associated with current through your body caused by contact or even just approaching it closer than you should. Then there's our, go ahead.
So what I'll ask what nobody else asked. What is a good practice if you have a coworker that's caught on and he's not able to
And he can't let go?
Yeah.
What do you do?
And I'd love to hear what the other guys say. You probably have answers, but
So
do you do?
some people say it depends on your coworker. That's the wrong answer. Okay, that's the wrong answer. Even if it's your ex-wife, you gotta do something. I'm just saying. So what you should do, short answer, is you should have right there at your work area a long conductive object designed to pull somebody off.
Non-conductive.
Did I say conductive?
Yeah.
Non-conductive.
Yeah, so they're
Device.
saying
NON.
2x4s. One guy said non-conductive. He mentioned that.
So 2x4s, absolutely not. You don't want to break their arms. You're just gonna make problems worse. You should everything comes down to pre-planning. If you're gonna be exposed, you better have some emergency preparations in place. A non-conductive object designed to pull somebody off. It's called a shepherd's hook, and I'm gonna show you a picture of what one looks like. Okay.
The best thing to happen would be able to turn the power off.
Right.
Then you wouldn't have
Yes.
to do it. Ultimately would be.
Yeah.
But
Yep.
that's generally not the way we go to it because somebody's getting shocked, right? Or receiving that kind of shock. Then the first thing you want to do is just try to help them get off. And again, you can't help somebody if you become part of the problem.
Yeah.
So that's where Dave's saying you have to pre-plan this out, have an idea together what you can do if something happens. Without pre-planning it, you may not be able to get the guy off. That's the hard part. You may end up watching him struggle and suffer because you can't get him removed from that part of that circuit.
And Mike's right. The best thing you want to do is shut the power off. But let's face it, sometimes you're at the point of work and the source, the circuit breaker, is in a different part of the building. Now what do? You failed to pre-plan. You don't have something there to pull some guy off. You grab a hold of him because you think you're Superman, and now you're caught up. Now we got two problems, two potential fatalities, right? So 2x4, I like where you're going with it, but no, we have to pre-plan and have the right device there to just yank somebody off. Done deal. I always tell everybody, if you fail to plan, you're planning to fail. And for those of you that have heard about the NFPA70E before, the biggest change I think they've made this version is we have to pre-plan for potential emergencies like that. That's now a requirement. Probably the biggest change I found, other than, a lot of battery definitions and, things like that. That's probably the biggest change this year. So good question. Pre-plan, non-conductive object designed to pull somebody off the circuit, or better yet, shut the power off. But that's not always the most efficient. You can't say, hang on, buddy, and run upstairs and whatever. You got to get him off right away. Yeah. He's dying. Yeah. Stay right there. That's insult to injury, literally. All right. Arc flash and arc blast hazards. What's an arc flash? Well, the NFPA70E defines an arc flash as a source of possible injury or damage to health associated with the release of energy caused by an electric arc. So when an electric arc fault occurs, there's a massive electrical explosion. Both the arc flash and the arc blast are separate byproducts of that electrical explosion. So the arc flash is the light and it's the heat from that explosion. And then it's followed by a pressure wave or a shock wave called an arc blast. Okay. And it's estimated that between 5 and 10 arc fault incidents occur every day in the United States based on the findings from the Bureau of Labor Statistics. I mean, this is every day.
So an arc fault is this either arc flash or arc blast. So the statistic was 5 to 10.
Yeah. Yeah, and I'm going to go over another statistic. But yeah, according to the Bureau of Labor Statistics, there's between 5 and 10 every day that occur in the U.S. Yep, every day. So what's an arc flash? It's the light and it's the heat that's created from an arc fault explosion. They say temperatures from an arc flash can reach as high as between 5,000 to 35,000 degrees Fahrenheit, and experts say that's about 4 times hotter than the surface of the sun. Crazy, right? 4 times hotter than the surface of the sun. Now let me give you something for your GWiz file. Arc flash incidents are not based on voltage. Okay, so if you're going to get into a panel and it's only 240 volts, your first thought is, well, it's only 240. How bad could it be, right? It's not based on voltage. It's based on the available fault current and how fast that overcurrent protection device that's feeding that panel is going to clear. The longer it takes for that breaker to trip that's feeding that panel, the worse it's going to be. The longer it takes for that fuse to pop, the worse it's going to be. Combined with the amount of fault current or current that's going where it shouldn't be going, okay, that's what makes up the arc flash. So don't think voltage is what you look at. That's part of the equation, but it's a very small part of the equation. Does that make sense? Yeah? Oh, okay.
They calculated how much current creates that blast or that flash? Do you have any idea?
Yes. So, yes. And we're going to get into it later on. But really smart people, smarter than I am, they can do a calculation and tell. It's called instant energy levels. It's measured in calories per centimeter squared. So we'll get into that. But engineers will basically, they can go in and they can look at everything built into the equation, give one measurement, say this is how bad the arc flash is going to be if there is one. And we'll talk about it.
You got a question regarding approach distance, which I
Yep.
imagine you'll cover.
We'll cover it.
Okay.
Yeah, we're going to get into approach distances. Absolutely.
So hold in there, Devin.
Yeah, hang tight, Dev. I'm not going to leave you hanging. All right. So what's an arc blast? The arc blast is the arc flash is the heat and the light. Make sense? Followed by a shock wave called an arc blast. The arc blast is a pressure wave or a shock wave created after the arc fault. Now, arc blasts can be strong enough to throw a fully grown technician to the ground or cause additional equipment damage. Arc blasts alone, just the shock wave alone, can crush bones. It can destroy vital organs in your body. And you don't even have to be right at the point of work. You can be a few feet away and it can blow you away. So we're going to talk about the boundaries related to arc flash and shock, okay? Because there are boundaries we have to maintain for both of these hazards. I'm going to look at you a lot because you're right there, just so you know. All right.
When you woke up this morning, you thought this would be a day like any other. You've been called in to do a quick job. Change a circuit breaker. No big deal. You've done it a million times before. You aren't going to rock the boat by asking for the power to be shut down. You'll just do it live. It'll only take a second. What you don't know is in the 6 months since this panel was last opened, dust has built up between live parts. There's a loose screw waiting to drop at any minute, and the insulation on the bus bar is old, worn, and about to crack. But that doesn't matter. Whatever the reason, you're working on live, energized equipment, and this is about to happen. So, what just happened? You just experienced an arc flash, an unexpected violent electrical short circuit where current flowed between the phase conductors, neutral, and earth. When that electrical arc fault occurred, the following things happened. The arc caused a superheated ball of flame to erupt around you, a fireball that reached 20,000 degrees Celsius in a fraction of a second. That's 4 times hotter than the surface of the sun, and it happened 30 centimeters from your face. The copper conductors vaporized and expanded up to 67,000 times their original volume, culminating in a shower of molten metal flying directly at you. The vaporized metals, smoke, and burnt components formed a boiling, poisonous gas that engulfed you and went into your airways. The pressure wave knocked you off your feet and into the wall behind you, collapsing your left lung. Thankfully, you survived. Your hands took the bulk of the heat blast, causing third-degree burns. You'll need skin grafts and months of rehabilitation. If you had worn the correct protective gloves, you could have reduced the risks and avoided serious burns. Your front and back were badly burnt, with second-degree burns across your chest from the initial blast, as well as a patchwork of first and second-degree burns where your shirt caught fire. If you had been wearing the correct arc-rated protective clothing, it could have prevented the arc flash from setting your clothes on fire. None of this would have happened if you had assessed the risks and de-energized the switchboard before you started work. But it's too late now. You will never regain the full use of your hands, so you may not be able to work as an electrician again. You'll be off work of any sort for months. On top of the injuries and lost wages, you'll also have fines to pay. If there are energized parts, expect the unexpected and protect yourself against arc flash. Always follow safe work procedures and wear appropriate PPE to reduce the risks of serious burns, injury, or death. Remember, the only way to eliminate the risk of arc flash is to choose not to work live.
And it is a choice. The job's always going to be there. It's going to get done with or without you.
When you woke up this morning, you thought this would be a day like any other. You've been cooked.
How do I go to the next slide?
So, was that in PowerPoint?
Mm-hmm. Let me go. So how common are these arc flash incidents? Well, another report published said that on average, there's about 30,000 arc flash incidents every year in the United States, resulting in almost 8,000 burn injuries or fatalities. If you think about it, that's almost 2 incidents per day in every state in the US. And the sad thing is, they're preventable. Turn it off, lock it out. In fact, the 70E requires us, OSHA requires us, and I'm sure your employer requires you to turn it off first. Turn it off, lock it out. Don't even be exposed. Because if you don't think it's going to happen, it happens. Almost 2 times every day in the United States. Some people survive and they're never the same again, and some don't. So the question is, how do we protect ourselves? Well, back in the day, many, many years ago, OSHA requested that the National Fire Protection Association develop a standard that would assist employers and employees in complying with the government's rules on the operation and maintenance of electrical systems. So the NFPA created what's called the 70E. So we have our building code. Within the building code, we have section 70, which is the National Electrical Code, right? 70E is the code we follow as electricians, so we go home safe every day. See, the National Electrical Code is the code we got to follow when we install the systems that you learn about every year in your apprenticeship. So when we walk away, it's safe for the consumer, right? But 70E is a code we have to follow, so we go home safe. That's the code we follow. And when we follow that code, we're following the OSHA, the MSHA, other regulatory agencies' standards. The 70 is not typically adopted via legislation. It's often used voluntarily by employers and employees to fulfill their obligations to OSHA. Usually, the sad thing is we don't find out if this has been followed until after something bad has happened, until somebody's been hurt or killed. Okay, but OSHA can come in, and if they have to do an investigation, I'm not going to tell you what they will do because I'm not OSHA, but typically what I've seen is when they have to come in and do an investigation, not an inspection, but an investigation because somebody almost died or died, there's a serious arc flash incident, they will look at our industry's most up-to-date standards, which is the NFPA70E, and they're going to see if we followed those standards or not. And if we don't, if we haven't followed those standards, they can cite us under what's called the General Duty Clause of the Occupational Safety and Health Act, which says Employer shall furnish to each of its employees employment and a place of employment that are free from recognized hazards that are causing or likely to cause death or serious physical harm to employees. So if anybody ever asks, are we required to follow the NFPA70E? The short answer is yeah, we're required. Okay? All right. As far as the 7E, it's broken down into 3 different chapters. And the first of the book has an introduction, explanatory material. Then we have chapter 1 that applies to electrical safety in the workplace. Chapter 2 addresses safety-related maintenance requirements. I swear I'm not touching it. It's just popping up. Or chapter 3 that modifies some of the requirements that we see in chapter 1. Now, in the back of the 7E, they have what's called informative annex. Those aren't requirements. It's just information to help us work safe and follow the requirements. Now, as far as chapter 3, that's where we find the standards for electrolytic cells, batteries, battery rooms, lasers, power electronic equipment, research and development laboratories, and things like capacitors as well. Now, in the NFPA70E, in years past versions, they always held just the employer responsible, okay? But as of 2021, I believe, the 2021 version, they now say the employer is required to establish and document what's called an electrical safety program, and they're required to train you guys on that electrical safety program. Now, though, they hold employees responsible for following their training and following the employer's electrical safety program. Okay. The 70 also requires, and really get this in, burn this in your brain, the employer, in the employer's electrical safety program, it has to require hazard elimination to be the first step when we need to control an electrical hazard. How do you eliminate an electrical hazard? What? Yeah, turn it off. Turn it off and lock and tag it out, right? It's required in Article 110.2A1 and 2. Okay, now here's the other thing. The 70E says energize electrical conductors and circuit parts operating at voltages equal to or greater than, here's the magic number you need to remember, 50 volts shall be put into an electrically safe work condition if you're going to be in what's called the limited approach boundary, which we'll talk about in just a sec. Or if you're not exposed, but you're interacting with a piece of equipment that could cause or create an arc flash explosion. Okay. Notice it doesn't say AC or DC. Did you notice that? It's 50 volts. If you're going to be exposed to 50 volts or higher, all the rules apply. Make sense? So let's break this down a little bit here. Okay. What's an electrically safe work condition? Well, the 70E says that's a state in which the electrical conductor or circuit parts has been disconnected from its energized parts, and it's locked and tagged in accordance with your facility or your employer's established standards. And then we test it for the absence of voltage. And sometimes, if we need to, we have to use temporary grounds as well. Part of that standard we just said or read said if you're going to be in what's called the limited approach boundary of exposed energized conductors or circuit parts at 50 volts or higher, then we have to turn it off and lock it out. So what's the limited approach boundary? Now, I know we don't have a whole lot of time today, but here's your boundaries. These are the approach boundaries that Dev was asking about. I got you, Dev. Okay. Now we have 3 boundaries. We have what's called an arc flash boundary. It's a red dotted line. And then we have what's called the limited approach boundary and restricted approach boundary. Those are the 3 approach boundaries we have to maintain if we're allowed to be exposed to 50 volts or higher. Take note that your limited and your restricted approach boundaries are for shock protection, not arc flash. Just the electrical shock that we talked about earlier, okay? So let's say you have your exposed energized circuit parts right here. The closest boundary to those exposed energized parts is your restricted approach boundary. We're not allowed to have anything conductive in that boundary. We're not even allowed to be in that boundary unless we're insulated or the equipment's insulated. Make sense? Then the outer boundary, shock boundary, this green one. And by the way, these boundaries aren't as big as what the picture shows. It's over exaggerated just to help you understand or learn the boundaries, okay? But your outermost shock protection boundary is called your limited approach boundary. So again, this standard says if we're going to be exposed to 50 volts or higher, and we're going to be in this limited approach boundary, we have to turn it off and lock it out. Now the 70 does have exceptions, okay? If it's infeasible, meaning we can't turn it off and lock it out because we got to test and troubleshoot. We can't measure voltage with the power off, right? We're electricians. Sometimes we have to test and troubleshoot. So that would be one exception. If we're going to perform ultrasounds, thermography, visual inspections, but we don't cross the restricted approach boundary, that would be some other exceptions. But short of those exceptions, we have to turn it off and lock it out if we're going to be exposed at 50 volts or higher. Now, I'll show you a table before we're done. It's called Table 130.4 EA for AC systems or Table 130.4 EB for DC systems. Those two tables in the 70 show you how to determine these boundaries. And I'll give you a quick little hint. Up to 400, I think it's up to 750 volts, your limited approach boundary is 3.5 feet. AC, for AC systems. Your restricted approach boundary is a foot. But because of our elevation, where we're at in Utah, the 24 version of the 70 says we have to make the restricted approach boundary a little bigger. So I tell people, double your boundaries. Just make them bigger. Like 2 feet for your restricted approach, okay? And like 7 or 8 feet for your limited approach boundary. Now these two shock boundaries or approach boundaries are completely independent and separate from your arc flash boundary. Your arc flash boundary, this red dotted line, sometimes it is your biggest boundary and sometimes it's not. Sometimes it's in here somewhere. It all depends on the study that was done by that engineer. Does that make sense?
Got a question from Caden. Does the dead front actually do anything when you are in a live panel and it arcs? For instance, some panels I am in, you can still keep the main breaker dead front cover on.
Does it actually do anything in an arc flash event? No, nothing. The panel's it'll go right through the metal. In fact,
It actually costs more because that'll vaporize that metal and it'll become
Molten.
Shrapnel.
Actually, it'll shrapnel.
yeah, now you got shrapnel flying at you 100 miles an hour on top of the arc blast, on top of the high temperatures that can be 4 times hotter than the surface of the sun.
Protect from an inadvertent contact on that, but if there's an actual arc blast or an arc flash, it isn't going to help you.
Yeah, exactly. And I'll show you some examples of exposure. That's one of them, actually. Now, the exception to what we just talked about, okay, the 70 allows normal operation of electrical equipment where a normal operating condition exists. Now, I think this is where a lot of electricians go wrong. They approach existing equipment, panels, disconnects, whatever, and they start opening them up and digging into them. What we need to do and what we're required to do is first make sure that we take a few steps back, take a few deep breaths, and look at it and see if it appears to have been installed correctly to the 70E, right? Or the 70, the National Electrical Code. We also have to look at it and see if it appears to have any evidence of impending failure. And I'll show you some examples of what that would be like. And we have to make sure it's been properly maintained. And to do that, we have to talk to the owner and ask for maintenance records, right? Because sometimes they haven't maintained it. Okay, so we can operate equipment normally with all the covers on. Okay, all the doors are closed, not just the dead front, but the cover of the panel. Okay, and we've made sure it's properly installed, it's properly maintained. There's no evidence of impending failure. We're using the equipment in accordance with the manufacturer's instructions, the listing and labeling things like that. Okay. So again, properly installed means it's been installed according to the National Electrical Code. Take a few steps back, a couple of deep breaths, and just look at it. You know, this is third year. You probably got a good idea if it's been installed correctly. Okay. Or properly maintained means that, again, it's been maintained in accordance with the manufacturer's recommendations and what's called the NFPA70E. A lot of people don't know that this even exists, but there is a code for maintenance. That's called the NFPA70E. And evidence of impending failure means there's no evidence for things like arcing, overheating. There's no loose, bound equipment parts. There's no damage, deterioration, and water damage. That's another thing with the 24 version. They want us to consider potential water damage. So this would be an example of evidence of impending failure. This is all burned up. Would you want to operate some of the circuit breakers on that piece of gear? Probably not, right? Doesn't look safe. There's been problems before. What if you walked up to a panel and the customer said, oh, yeah, we maintain this all the time. But you see this, does that look like it's been properly maintained? There could be a squirrel in there. I took a cover years and years ago when I was an apprentice. Cover years ago. And the building power is completely disconnected. But I took the cover off of a transformer, and I'm telling the truth because I see the look in your face. Took the cover off a transformer, there's a squirrel between the phases of the transformer, just fried. So we need to look at documentation. If it wasn't documented, they probably didn't maintain it.
It hasn't been maintained unless for some reason they can prove to you that they have. Because 90% of the people don't know they need to maintain it, and they don't maintain it. So you can almost guarantee it hasn't been maintained.
Yep.
And to that point, I mean, as simple as the overcurrent protective devices, the manufacturers tell you to instruct you to cycle them, and nobody knows that. They instruct you to cycle them every X amount of days or whatever.
Nobody does that, really?
Nobody does it. Nobody knows it.
What if you walked up and didn't look properly installed, maintained, and you opened it up and you saw this? You think that could cause, if you started switching things off and on, that could cause an arc flash? Guarantee you it will. Okay. The 24 version of this. The 70E now wants us to consider potential water damage. So if you came up to something like this, okay, and you saw condensation on the outside, what's going to be on the inside? Probably more condensation, right? And if does water and electricity mix? No. It's a bad thing. It's a bad thing. Okay. Now, I always tell people you have to ask yourself, even after you've performed lockout tagout, am I exposed to any stored energy? So what does exposed mean? I'm glad you asked. The 70 has two definitions for exposed. The first one is capable of being inadvertently touched or approached nearer than a safe distance by a person. It's applied to electrical conductors or circuit parts that are not suitably guarded, isolated, or insulated, or on or attached to the surface or behind panels designed to allow access. So if you could accidentally make contact or even approach too close to an energized circuit part or conductor, are you exposed? Yeah, good answer. Yes, you're exposed. So here's some examples of exposed. You can see this is an MCC bucket. They turned it off. Let's even say they put a lock and a tag on it. Are you still exposed to any live energy parts in this bucket? Absolutely. All you got to do is look at this arrow, right? The line side of the breaker is still attached to the main bus on that gear. So if the whole bank, if the main for that whole bank is still turned on, you're still exposed. Once you get a tool out, screwdriver, you're probably going to be tempted to make an adjustment if you see something loose, and bam, there's an arc flash. You're exposed, even with it turned off. That's why I tell people to take a few steps back, a couple deep breaths, and ask yourself, what am I exposed to? Now that I've turned it off and locked it out, what could go wrong? Okay? Here's another example. disconnects, right? It's turned off, but you got the line side there. You're still exposed. Or how about this? This is what somebody brought up just a little bit ago. Take the cover off, you got the dead front on. One time I walked on a job years and years and years ago, brand new foreman. This wasn't the panel, but it was the one I saw was just like it. The cover was off, dead front was on, and there's a pile of seismic wire for a T-grid ceiling sitting there underneath the panel. And I asked the foreman, is this live? And he said, yeah. That's okay though. I got the dead front on. And I said, well, okay. What if the T-grid contractor goes to pick up a pile of that seismic wire? Do you think that seismic wire could contact these energized conductors or circuit parts behind the dead front? He goes, oh yeah. You left it exposed. You left a hazard sitting there, and somebody could have been killed. So even when you take the cover off, but you leave the dead front on, if that panel is energized, you're exposed. Does that make sense? Things can go wrong. We're exposed when we're taking meter measurements, when we're testing and troubleshooting. We're even exposed when we rack large breakers on in and out of equipment. Now, you can see here, you're not exposed. There's no like energized copper circuit parts or conductors here, but he's interacting with the equipment in a manner that could cause an arc flash, right? You're racking a large breaker on and off of an energized bus bar. You gotta ask yourself, what could go wrong? A lot. It could fail, and it does. Now, before we get into much more, let's just look at burns real quick. The Safety Council has categorized burns in 3 categories. There's first-degree burns, second-degree burns, and third-degree burns. First-degree burns involves just a burn to the outer layer of the skin. There's no blistering. It's like a bad sunburn. It's going to be red. It's going to swell, and it's going to hurt. Second-degree burns, that affects the inner layer of the skin, so now it blisters. Okay, when you have a burn and there's blistering occurring, even with bad sunburns, and you got little blisters, that's a second-degree burn. Third-degree burns, they can appear like a charred or a white waxy leathery appearance. You can heal from a first-degree burn and a second-degree burn naturally, but you can't heal from a third-degree burn. That's where the doctors got to go in and they got to do skin grafts. It's going to take years, for the treatment and years to recover, and then you'll never be the same again. Now, here's something for you, G-Wiz. Wow. Do you think arc flash suits, if you're an arc flash, you're wearing an arc flash suit, do you think it's going to protect you from burns? Exactly. That's why you know all the answers, because you're here. No offense. Anyways, if you're wearing arc flash PPE and it's the properly rated arc flash for the amount of, exposure and calories per centimeter squared of arc flash, okay, it's designed to hopefully limit your burns to a second degree and hopefully keep you alive. So if you're an arc flash and you're wearing the properly rated arc flash for the exposure, okay, in that equipment, you're not going to go home and pop a cold one and say, guess what happened at work, honey? It's not going to happen. She's going to go to the hospital. She's going to be visiting you there. It's only designed to hopefully keep you alive and hopefully limit your burns to your whole body burns to a second degree. Crazy, right? A lot of people wear arc flash PPE with a false sense of security. This is a bad but a second degree burn. It's red, swollen. You can see the blisters here. This is a third degree burn. That person's not going to heal naturally. He's going to need lots of skin grafts, and they can't just do a whole sleeve. They do little parts at a time. They do a little part, it has to heal. It takes a long time. They do another part, it has to heal, and on and on and on and on and on. And the recovery takes years, and you're never the same, ever, for the rest of your life. No wonder OSHA wants you to lock it out. No wonder the 70E says you have to lock it out. No wonder your employer wants you to lock it out. It's just not worth it. And by the way, pain meds, it's not going to take the pain away. It just helps you deal with it. Make sense? Scared? Did I scare you enough? I did a class and there's a couple of union hands in there. And they said, I should just go work at a grocery store and bag groceries. They're pretty scared. Now, one of the big changes in the 2015 version of the 70E was they said, we got to plan our workout. We got to utilize risk assessments. But the problem back then in 2015 is they didn't tell us what they wanted to see on a risk assessment. So you could literally take a piece of cardboard and write work safe and go home safe. Bam, there's my risk assessment. But in 2018, they made a major change and said, okay, this is what we want to see on a risk assessment. We have to look at the potentials, like what the hazard is, how bad the outcome's going to be. Is it going to be a first degree, second, third degree burn? Okay. And put all the controls in place and reevaluate to see what the outcome could be after all our controls are in place. And when we do that, they came up with what's called a hierarchy of risk control. And they say we have to utilize this hierarchy of risk control when we're planning out our work, before we take that cover off, before we are exposed, okay? And this is a table or a graphic that helps us look at the most effective means of controlling the hazard and the least effective. Check out the least effective method of controlling an electrical hazard. PPE. PPE is our last line of defense. It's only designed to keep us alive. Hopefully, right? Hopefully limit our burns to a second degree. So before you throw that arc flash suit on and think, yeah, I'll be good. No, this is your last line of defense. Okay? We talked about it. Our first line of defense is eliminating the hazard. Physically remove it. Turn it off. Put a lock and tag on it. Right? And there's other things in the middle, like owner substituting, old gear for new, updated gear, like that might be ARC rated. There's things like risk assessments. We have to do them, but it doesn't really change our behavior. Sometimes people can pencil whip paper, right? They want the first in the hierarchy is turn it off and lock it out. As far as planning goes, there is a specific procedure that we have to follow when we plan out our work before we take any covers off. Number one, it says the plan has to be completed and documented by a qualified person. In just a sec, we're going to talk about what that means to be a qualified person. And we have to include the following in our documented plan. We have to have a description of the job and the individual tasks that each person's going to do. We have to identify the electrical hazards with each task everybody's going to do. We have to perform a shock and arc flash risk assessment. We have to plan out all the work procedures involved, the special precautions we got to take, and identify energy source controls. And the big change this year, the 24 version of the 70E, is we have to have an emergency response plan too, documented. Okay. So what does it mean to be a qualified person? The 70E defines a qualified person as one who's demonstrated their skills and knowledge related to the construction and operation of the electrical equipment that needs to be worked on and installations, and they've also received safety training to identify the hazards so they can reduce the associated risk. Now this, what we're doing here, that's not your safety training for a qualified person. We're talking some comprehensive, extensive training. Does that make sense? I don't give you a drink, of water through a fire hose. We spend like a day or three and train. Okay. So you have to be a qualified person. And then we also have to prepare for emergencies. So is there somebody there that can perform first aid CPR? Where's our emergency equipment? Okay. Do we have the right equipment there? Where's the nearest phone or means to communicate with EMTs or emergency services? Do we know where the fire alarm activation stations are? Can we guide emergency services to our exact location if something goes wrong? Okay. Do we have equipment like fire extinguishers, AEDs? Now that shepherd's hook we talked about that we should have in our work area to pull somebody off if somebody gets caught up. Remember that? Hopefully you do, because it was only like 40 minutes ago. That's this right here. This is an insulated device, and it's been designed and engineered to pull somebody off a circuit when they're caught up. You grab your coworker, you're caught up too. Okay? And no, we don't want to get a 2x4 or a piece of conduit because we really shouldn't break their arms, to get them off the circuit. If you don't have the right stuff there, you shouldn't even be exposed. You shouldn't even take the cover off. Fire extinguisher, in case something's on fire after the arc flash. First aid kit, somebody that can use an AED if there's one nearby. And do we have a way to call for emergency services as well? The 70E also requires that the person in charge hold what's called a job safety briefing before we start our work, okay? That's basically a safety meeting. That's where the boss goes over our documented plan with everybody that's going to do the work, goes over our emergency preparations before we do anything. And if our work changes, Article 113 of the 70E says, if there's any change in the work we pre-planned, we got to stop, replan, have another safety meeting before we continue on. I'm going a little quick here, but does it make sense?
You're doing great.
Okay. Let's talk about meters for a sec. The 70E says that only qualified persons shall perform tasks such as testing, troubleshooting, and measuring voltage on electrical equipment whenever you're exposed. So you remember what a qualified person is, right? Somebody that has had extensive safety training and they've demonstrated their knowledge. They're the ones that are allowed to troubleshoot and use meters. Okay? The 70 also says test instruments, equipment, and their accessories have to be rated for the circuits and equipment that they're utilized, approved for the purpose, and used in accordance with the manufacturer's instructions. The 70 also says that our test instruments, equipment, and their accessories shall be designed for the environment to which they're exposed to and the manner they're going to be utilized. And if test instruments and it says test instruments and equipment and all associated test leads, cables, power cords, probes, connectors have to be visually inspected by the qualified person for any defects or any evidence of damage that might expose that qualified person to an injury. And if it is defective, we have to take it out of service and have it fixed, repaired by somebody that's qualified to fix or repair our meters. And here's a real important one here. The 70 requires that when test instruments are used for testing for the absence of voltage on conductors or circuit parts operating at voltages equal to or greater than, here's the magic number again, 50 volts. The operation of that test instrument has to be verified on a known voltage source before and after the absence of voltage test is performed. So what are they saying? What they're saying is if we're going to be exposed to 50 volts or more, we have to do a pre-test on our test instruments. So we have to go to a known voltage source like an extension cord plugged in or a receptacle on a wall and do a pre-test and make sure that meter is reading properly. Okay. Then we go do our test for the absence of voltage. And then we have to do a post-test. We have to go back to that known energy source and do a test again on our meter to make sure it's working correctly. Okay, does that make sense? Now, Fluke has a cool thing out. I just really like it. I don't get endorsed or paid by Fluke. I wish I did, but I don't. It's called the Fluke Proving Unit. This is your known energy source right here. You can hang it up at your work area. You can test your meter, do your absence of voltage test it again on the proving unit. Now you know your meter's working correctly. And they make them for different types of testers, for amp readers, meters, probes for meters, things like that. And that also includes your induction tester. or idiot stick. You brought that up a little earlier. Before we test, a circuit, we need to make sure that we test it before we even touch it. What's the best way to do that? Use an induction tester. Now, somebody said earlier they don't like them because they can give you inaccurate readings. Somebody said that, right?
Yep.
They're right. It can give you a false reading, but here's how it works. If it's working correctly, it's going to give you a false positive, not a false negative. Okay, so when you have two conductors,
Draw just barely to the right of the screen. You'll be able to see that.
right here,
Yep, so stay on the left
right here.
third of that.
Okay.
Yep.
So let's say you have two conductors, conductor A and conductor B. Okay. So you have conductor A, and then you have conductor B. Let's say conductor A, that's energized. Okay. B is not. With me so far? B's not energized. If you take your induction tester to B, it's probably going to say that it's energized. It's going to give you a false reading. And the reason why is because when you energize a cable, it creates induction or a magnetic field around that cable. And some of that induction will transfer over to the other one, giving you a false positive if it's working correctly. Does that make sense? We'd rather have a false positive than a false negative, right? Because that's going to make us more aware. Holy crap, this shouldn't be live. You should be stopping and investigating now. Does that make sense? But the induction testers are really good to use because that'll tell you after you've performed lockout tagout, if that thing lights up, that's a red flag. Maybe you turned off the wrong circuit. You got to investigate. See how that works?
Schedules are not always right.
No, they're always right.
I have a perfect real life example of what you've drawn in Romex, and this happens in EMT as well, but you're on a three-way switch. I know that with 14.3, your both travelers will have that induction, that false positive on it.
Yep, exactly. Two conductors in a conduit, two conductors in a cable. Yep, can happen. So yeah, whoever said they don't give you accurate readings, absolutely 100% correct. But if they're working right, it's going to give you a false positive. And when you're testing for the absence of voltage, you want that red flag to pop up. It makes you more cautious. It makes you safer. Does that make sense? If it lights up, you stop and then go get a qualified person to help you make sure it's safe. Somebody that's been trained and somebody that can help you make it safe. Somebody that's demonstrated their knowledge prior. Okay? Now, usually after this, I play a video. It's by Fluke, and it goes over the different categories of meters. It's about 20 minutes long, so I'm not going to play it. However, I'll give it to Mike, okay, the file electronically, and you can get it from him. But it's a really good video. And one of the important things with that video is it talks about the category ratings and the testing agencies that test these meters. In our company, we only allow a category 3 and a category 4. Category 3 for inside distribution, like things we work on as electricians, okay? Category 4 for outside connections like utilities, okay? Now, the categories are real important. If you're not using at least a category 3 or a category 4, you're not going to be protected. See, sometimes things called transient voltage or spikes occur. If there's lightning outside, or if the power company is doing switches for just fractions of a second, hundreds of thousands of volts could go through that circuit, and it can blow that meter up and cause a gigantic arc flash explosion right there in the palm of your hand. A good quality meter will have on the back of the meter a UL stamp and then either a TUV or another European testing facility. Look at the back of your meter. Make sure it's got at least two testing facilities stamped on the back. That means they've tested it for things like transient voltages and spikes. Okay? If your meter says category 1 or category 2, that's not for construction. That's not going to protect you. And then look at the back of your meter. Just to give you a little example, real quick. We did a qualified person training. We had a guy bring his own meter in. It was one of those Klein meters from the Black Friday sale at like Lowe's or wherever. And he took the cover off, pulled it, looked at the back of the meter. Didn't have a UL, didn't have a TUV, didn't have any testing facilities on there. That means that meter hasn't been tested by a laboratory to make sure it's going to protect you if there's a voltage spike or transient voltages in that fraction of a second. Isn't that crazy? And Klein's a good name.
Yeah.
That's a big brand. So I guess what I'm trying to tell you is I'm not an advocate for fluke, but I'm going to tell you this. You get what you pay for. You're going to save money. You're taking a big risk. It's good to get a deal, okay? But don't go to, Harbor Freight and buy the one that says industrial strength and it's got diamond, plate, box. There have been people literally that used those that died because there was a transient spike in a fraction of a second. Like in one case back east, the guy was testing a 480 volt circuit in a mall and there was a spike. In just a fraction of a second, the meter blew up, caused an arc flash, killed him, and the fire marshal standing right behind him because he was using a cheap meter. Crazy, huh? Yeah. So if you want to watch that video, I'll give it to Mike, and he can give it to you.
We'll give it to Josh. He'll post it on the classroom, and then they'll have access to go in
Okay.
and watch it from the classroom.
So remind me tomorrow, I'll give it to you. That's normally where we play it. So again, an electrically safe work condition is where we've turned it off and locked it out, right? That's what we have to do. It's a requirement if it's 50 volts or higher, okay? Real quick, our lockout devices, the 70E says that the employer has to supply the lockout devices and they have to be readily identifiable as a lockout device, and they can't be used for any other purposes. So you should be able to look at a lock and know that somebody locked out a circuit or source of hazardous energy. You should be able to know that that's the case and that lock isn't secured. Does that make sense? And you can't use them for any other purpose, okay? So you can't lock your pack outs with them or your wave runners at home or whatever. Now, I'm not going to read through all the steps for lockout tagout because we don't have time. But in Article 120.6, that's where you find all the required steps for lockout tagout that your employer should have in their their electrical safety program that we talked about earlier today. Okay. There's a lot of steps. One of the things I want to show you, see if I can go back here.
Question, are there consequences for removing somebody else's lock, like unauthorized removal?
Yeah,
You're working on it and they get that.
yeah, it's
Early
called
termination.
it's called attempted murder. Really?
Attempted murder.
Yeah.
Really?
Yeah. If you're going to cut somebody else's lockout device off, then you have to make sure that there's a process you're following to make sure that it's safe, that they're not there and nobody's going to get hurt. If you don't do that, yeah, you could kill somebody. Yeah, manslaughter, attempted murder, whatever. Yeah, it's bad. Good question. Don't cut somebody's lock off. Your employer should have an abnormal lock removal procedure where they go through a whole bunch of steps. That includes inspecting the area, getting a hold of the person. If they're home in bed, they've knocked on their door, said, get back to work and take your lock off. I mean, all this stuff. And if they can't get a hold of the person, they got to cut it off. They've gone through all the steps to make sure that the person's gone, he's not coming back, at least for a while, and that it's safe for him and everybody else. Yeah, very good question. Article 130 of the 70E is where we find the requirements to perform energized work. For the sake of time, I can't go over all these requirements. The key points you need to remember is that magic number 50 volts. If it's 50 volts, notice again, it doesn't say AC or DC. If it's 50 volts or higher, all the rules like the planning we talked about, they apply. Okay? And only qualified persons are allowed to do that work. Okay? And most of the time, you have to have what's called an energized work permit too. Okay? That's part of our planning documented process. There are some exceptions to, the energized work permit. Again, if we're going to test or troubleshoot, we don't have to have the permit, but everything else in our plan applies. Okay. Some of the exceptions, like I said, testing, troubleshooting, thermography, ultrasounds, or even just visual inspections. But if you notice here, where they're exposed, what do they have on? They have on their arc flash PPE, and they have on their insulated gloves for their shock protection. Okay. This is that table I told you about, 130.4 EA. This is the table that's in the 70E that helps us determine those two approach boundaries for shock, our limited approach and our restricted approach boundaries. Okay. If you look here in this column, it's all based on voltage. Your shock boundaries are just based on voltage, which arc flash boundaries aren't. So if you look at this table, between 151 and 750 volts, if it's an overhead conductor supported by a pole, our limited approach boundary is 10 feet. Makes sense, right? Got to stay 10 feet away from overhead conductors supported by poles. But if it's not, if it's anything above and beyond that, our limited approach boundary is 3.5 feet, and our restricted approach boundary is 1 foot. Now, one of the changes in the 2470E is they say that we have to make this boundary if we're going to be at an elevation of 3,000 feet or higher, and we are here in Utah, right? We're at 42, something like that. So I tell people these boundaries, make them bigger, just double. Okay, that makes sense. Now, as far as determining our arc flash PPE, that's probably what you're wondering. How do we know what level of arc flash PPE it is we got to wear? Number one, you got to be a qualified person, so you have to go through extensive training that talks about how to choose that. Okay, but for your GWiz files, there's two methods. One method is there's a table we can look at in the 70E, and it'll give us, the level of arc flash PPE it is we got to wear and our arc flash boundary. The other method is what's called an analysis method, where we hire an engineer. He looks at the entire system, does a study. He puts a label on each piece of equipment, and that label tells us how bad the arc flash is going to be and what kind of PPE it is we have to wear at minimum. Does that make sense? But let me tell you something. As far as your table method, this is what the table looks like. The 70E says that this method does not cover an arc in a box type of setup where the incident energy is focused and the multiplier effect is involved. This method is only suitable for open air arcs like battery systems, DC process systems in open rooms. So I always tell people, don't use this table. Go by the analysis method where somebody like an engineer has gone through and done all the calculations and they put a label on the equipment. But that's something you learn in qualified person training. Okay? So don't use that. And let me show you why. Here's what the table looks like. It's a close-up. In the table, it's got equipment on one column tells you your arc flash PBE category, level of PBE you should wear, and your arc flash boundary, that red dotted line. But if you look here, it says parameters for this 240 volts and below piece of equipment. It says you can't be exposed to any more than 25,000 amps of fault current, and overcurrent protection device feeding that panel has to clear within 0.03 seconds or 2 cycles. So my question to you is, you go to get a 240 volt panel, are you going to know what these parameters are? No, you're not. You're just not. You're not going to know. And remember, this does not cover arc in a box type things like panels. Does that make sense? So don't use this gear unless you know, you have to know for a fact what those parameters are in the gear in real life. Okay? So instead, what we're going to want to use is the analysis method. Now, some instructors will say for molded case circuit breakers, they typically will follow those parameters. Okay? And the notes underneath that table give you some examples here. The thing I have a problem with, number one, is I don't think anybody's going to read this in the field. They want to get the job done. The second problem I have with this is, see where it says 1.5 cycle of fault clearing times typical for molded case circuit breakers rated less than 1,000 volts, blah, 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 blah. What does typical mean? Does it mean always? That's the problem I have. I don't like taking a chance when it comes to electrical hazards. Remember the burn pictures I showed you? Imagine that third degree all over 70%, 80% of your body. And you live. You can't go to the bathroom by yourself. You can't eat your dinner somebody's got to feed you. You're not going to look the same. You got to wear a mask for years to cover the burns, including your face. That means you can't go to the bank. You can't walk into a bank with a mask, Okay. So that's why I personally don't. Yeah, exactly.
I remember.
And when you do, if you know the parameters and you can use that table, these are the different ratings of arc flash PB. Now, real quick, arc flash intensities rated or measured by calories per centimeter squared. So what's a calorie? Okay. 1.2 calories is a second degree body burn. Okay. Now don't really do this. Okay. Especially people at home. Keep your lighter in your pocket. But hypothetically, if you took a lighter, you lit it and put your palm of your hand under the hottest part of the flame for about 1 second where you get a second degree burn blister, that's 1 calorie per centimeter squared. 1.2 to be exact. Now, if the label on the equipment says, the engineer says, well, this intensity in this panel is going to be 5 calories per centimeter squared. Take that example and times it by 5 over 80-90% of your body. That's a bad burn, right? That's where you say, yeah. Yeah, it's a bad burn. Okay, so whenever you see calories per centimeter squared, the different arc flash categories are rated for different intensities of an arc flash if it occurs. Okay? And table 138.7C15C is a table to choose, is the table where, you can find your level of arc flash PB. But remember, we can't use that table. We have to use the analysis method, right? Because we're not going to know the parameters. So the analysis method is a totally different table. In fact, the analysis method says that if you're going to be exposed to incident energy levels of 12 calories or greater, you have to wear the arc flash hood, okay? Or the astronaut hood, like one of these. So it's a different method. It'll give you all the information on that label. In fact, here's an example of what a label is going to look like. Make it big enough. So if you look here, this is an example of a label that you should see on every piece of equipment out there in the field. In fact, the 70E says the owner of the equipment is required to put a label like this on every piece of equipment. They have to maintain it, and they have to maintain the backup documentation that the engineer gave them for their study. And if you look here, it says, what's that? Yes, 5.7 calories per centimeter squared. That lighter example, times that by 5.7. That's how bad the arc flash is going to be for that equipment that this label's on. And it tells you your boundaries for shock, tells you your arc flash boundary. Keep in mind that arc flash boundary is calculated at a distance where if somebody that's not suited up in their arc flash PB is standing right there at your boundary, this says they will only get a 2nd degree body burn. That's bad, right? What's that unprotected person going to do if they get burned up over most of their body? Huh? Well, if they live. Or if they don't, what's their family going to do? One call, that's all. They're going to sue you and your employer, everybody involved.
Yeah.
So here's my point. If that ever, whatever that distance is, like double it at minimum or triple it. So nobody that's not wearing arc flash PPE, so they won't get burned up. So they'll be okay. Okay. The last thing I'm going to show you.
Who puts these labels on?
So the owner's required to do that.
The owner
Of the equipment.
Oh, okay.
Of the equipment.
So generally speaking, that would fall to you as an installer.
Depending.
To do that work.
Well, we're under contract, but then once they
They have to maintain it.
Yeah.
But it has to be in the spec for you to do it. It's not in every spec, but
Right.
the owner's required to do that. So.
Depends on whoever paid to have the test done. A lot of times, will fall in your scope. You'll have a firm put together, sticker.
These
Print them out,
labels
give them
and
to
you-
you, and then you'll go on site and put them on.
Neat.
Anyway, I think we're done at a time. But real quick, just remember a couple things. It's not just the ball of fire. It's not just the heat, and that shock wave that's going to crush your bones and destroy your vital organs. When in that fraction of a second at those high temperatures, that solid bus bar is going to vaporize from a solid to a vapor, and all the metal fragments are going to fly at you at hundreds of miles an hour, literally. And do you think that arc flash PPE suit is going to stop those metal fragments? No, not unless.
It's not a Kevlar suit.
Yeah, it's not Kevlar. Okay, it's going to go right through it into your body. And think about this, if you happen to be inhaling that fraction of a second, where's all that stuff going? The high temperatures in the shrapnel, in your lungs, in your airways. Now you can't breathe for the rest of your life. And if
which is short. You can't breathe for the rest of your life.
Yeah.
You're lucky
That's a
enough,
long
you'll be
rest
able
of your life, though, if you can't breathe.
You'll be able to use oxygen.
Okay.
Lucky.
Any questions? Online people, do you have any questions? Lastly, I'll leave you this. Don't have emergencies. And what I mean by that is don't just rush into something where, try to save the day. Okay? If something happens, if it goes down, if they need it fixed, plan it out. We're required to. If you fail to plan, you're planning to fail, that's where people get killed. They think, I'll fix it, and they get blown up. Okay? It's not worth it.